This is pictures of recent field projects with students. The field project is usually a deployment of 3 students with a host company or host client who act as a consultant on an agreed upon issue important to the company, but really not, if possible, not on a critical path. They are not like undergraduates. You do not have to hold their hands. They actually will write a letter of proposal. They'll actually create a work plan and they'll execute that work plan. They will need to meet with you once a week just to make certain that they're staying on the right road more than anything else. So it's different than perhaps an undergraduate exercise, an undergraduate summer job. These people are fairly independent. They just need some questions answered about which way the analysis should go. As I said, we have a methodology. We're teaching that methodology this fall, in the fall semester. And we actually end up with looking at just about all of these steps in some form or fashion, teaching the students the kinds of end products that to create. We also run a simulated field project, we call it BevCo, so that the students really do get a sense of what that project is, what a field project is, and how to go about it. We've had a good deal of experience. These are most of the companies we've actually done field projects for. We've probably done nearly 100 field projects in the time since the inception of the program, in a range of industries, a range of company sizes, all the way from a sole entrepreneur to a early stage company to a big corporation. We've done them all. And again, we use the same methodology, whichever client we're working with. This is a typical schedule in the spring semester of a field project. It is fairly fast paced, goes about 15 to 16 weeks, the length of the semester. There's a couple of key activities here. There's where we meet the client, they'll interview and actually write an LOP, a letter of proposal based on that interview as to what the project should be about with your agreement. And then there's the project reviews, which are key milestones where they stand for up to an hour and present their results at that point in the project, as in the middle of the project, but also at the conclusion of the project. Okay. Oops. These progress reviews are important professional development opportunities for our students, learning how to stand before people they don't know and trying to be persuasive about what they found out in terms of answering the central issue of the case. We typically have faculty review their presentations before they're delivered to clients. And again, it is in and of itself, it's a growth opportunity for our students to be able to stand up in front of an audience of people they don't know so well and attempt to be persuasive about what they found out. Okay, so that's the broad scope of sort of what it is. Let's talk about a couple of cases of field projects we've done that are indicative, though not comprehensively, indicative of what a field project is. The first field project I like to talk about is one we did for SRI.
Hey, Keith, maybe stop right there about the program. Are there any questions about that? Maybe just while they're fresh in your mind, any questions about what the PDP is?
One question, you gave spring as an example time frame. Is that the intended time frame for this particular version?
All projects are executed in the spring.
Great, thank you.
Okay. Let's go ahead and talk about field project case studies. We did a project for SRI about 4 years ago. SRI's flow chemistry technology, and I'm going to explain what that is in a moment. They call it Sinfini. Sinfini, automatic synthetic chemistry platform. Flow chemistry, to be clear about what it is the notion of, there are kind of 2 broad ways you can actually conduct a chemical reaction. You can actually make one happen. You could take a batch approach, that is either a vessel or even a beaker on a desk, and mix all of the reactants in that vessel or beaker and conduct the reaction that way. Or you can introduce the reactants by having them flow through conduits and actually introduce those reagents, where you choose to, and even process either heat or separate or whatever you choose to call it in a flow chemistry approach, which is indicated in the diagram on the upper left. The advantages of over batch operations: faster reaction, cleaner product, fewer products that you don't want created, safer reaction, quicker optimization, easy scale up is challengeable, and it actually does integrate various processes sort of on the fly. So flow chemistry is the technology SRI was using. SRI's Sinfini flute suite included two big components when we work with them. One was the artificial intelligence component, and the purpose of the SynRoot component was to be able to craft alternative pathways to create a typically complex small molecule. They say that basically their AI, when given a thermodynamically stable molecule, the AI component of what they had could craft 10 alternative pathways in about 10 seconds. These are very complicated synthesis pathways. That is not what we worked on. That part existed and has been developed since then. We worked on the AutoSyn platform, this notion of the development system, synthetic roots, analytical chemistry, actually creating the molecules that they sought to create on behalf typically of the drug industry. This is a prototype of what it looked like, what the AutoSyn module looked like. This is the actual flow chemistry module that what it looked like at the time when we worked with them. It's developed since then. And the central issue they were asking is there an optimal commercialization path for Sinfini flow chemistry technology? How should we commercialize this? And SRI has a fairly good amount of experience in commercialization. So this was a challenge with a high bar that we had to come up with things that perhaps they hadn't thought of. Okay. So let's talk about this specific product. The problem statement in this case with SRI is that their flow chemistry technology platform used for, this was the choice they made, focused on synthetic non-natural polymers. These are molecules or components that actually mimic biological entities like proteins. They asked us to focus on that. And with automation and scale up, they could produce these kinds of very complicated molecules and do it in the space of 1 week versus the traditional approach by contract research operators that takes 6 to 8 weeks. Okay, so they were claiming this is a real possibility. They'd like us to actually develop an understanding of the market potential in this NNP, as well as the commercialization path. So this is a partial view of our analytical approach to that particular problem. How do they actually go to market? We made a bottom-up estimation of the market size. We used an online pricing survey, a very cleverly designed online pricing survey by the students, to determine where this technology had to perform relative to contract research organizations, which would be its major competitor. We conducted drug industry interviews with the very elite of the drug industry to determine whether or not this offering would be received well by them. And we actually came up with alternative business models for the client, and we provided those results in the 15-week survey. Let's take a quick look at some of the analytical approach. In terms of the market size, this is a very common analytical activity teams take on. They start bottom up and come up with the various factors and actually multiply them out to get the accessible market in total. There is sometimes some segmentation, but mostly it's the overall size of the market and maybe some adjustment for time. So the market is 5.5 billion in rough numbers based on a bottom-up assessment. This is the survey that they sent out with the guidance of the client for this particular molecule, a chloride version of fluconazole. They actually sent out basically a request for a proposal to 20 contract research organizations who responded with what it would cost in terms of per unit mass and how much time it would take to get that piece of work. They initiated this work. They came up with that idea and pursued it to great effect. So there is the name of the companies, but and the weight. But what we found useful to do, what the team found useful to do, was to include the duration. That is the price each of these entities would create this compound and how long it would take for SRI or anyone else to get that compound back. And you see the locus is in that blue circle there, where most of them are that are relevant. And the team identified that a likely competitive space for Sinfini, given its profile, is in the rectangle blue up in the left area. So this was an important piece of information about how well Sinfini had to perform if it was going to justify certainly a premium pricing in its market. The team also went out to really understand the drug industry's response to this whole Sinfini offering. They interviewed Merck in depth, Novartis, and Revolution Medicine, and they talked about Sinfini in terms of automation, speed, flexibility, simplicity, reproducibility, the AI software, and cost. Let me summarize a couple of findings that were interesting. Automation, flexibility, and reproducibility were very important to the drug companies. Not so important, and they were skeptical about, was the AI software, which is a little bit of a surprise. They think human beings have to be involved. Well, we were talking to organic chemists, so that's what they said. And cost was not an issue. They had no concerns over the price tag they'd have to pay for this kind of equipment. Okay. So that was sort of an overview of the kind of analytical approach. At the end of the day, the team had to make recommendations. They made the recommendation that immediately, right at this point, given where they were several years ago, that they start as a service business, that they compete directly with the contract research operators, that they build reputation and trust of the drug industry relative to those CROs, and that would prepare them after a period for long term, which is where they really wanted to go. They want to be equipment salesmen with follow-up services and both consulting and equipment repair and equipment provision. So this was sort of where the project ended at that time. It was a great project. The head of the biosciences division was very effusive in sort of his praise for what the students did. And they did it again without, day-to-day guidance. They did it with a weekly phone call with SRI to make certain that things were still on track. Any questions about, I'm gonna go to another one, and then we'll finish. Any questions about this project? Any of the analysts, analytics, you find curious? Okay, great. Maybe there'll be a question at the end. Let's take up the second issue, which has a, by the way, on the Sinfini, if you go to the SRI website, they are still trying to commercialize. They're looking for commercial partners. I think that does include the drug industry, but as far as I can tell, they are not yet moved into either the service model or the equipment sales model, but they are absolutely out publicizing at various conferences and conventions this technology. 4D Molecular Therapeutics is an interesting company. It's a company started by UC Berkeley professor Dave Schaefer. It's a company focused on the gene therapy business, and their primary contribution to that is the development of customized or engineered viral vectors, that is delivery entities that actually could deliver either drugs or genetic material to specific types of tissues. So the central issue is, how should 4D Molecular Therapeutics, and this is at the very start of their company, approach and target the market and set the market priorities? There are a number of genetic diseases that they could focus on, but they had limited resources. The company is based on the Nobel Prize winning idea and technology of directed evolution. When we talk about directed evolution, we're talking about a number of vectors, millions of viral vectors on the left side of this screen, differing in configuration and the like, exposing those vectors to various tissue types, eye, heart, muscle, lungs, etc. And over time, through iteration, really figuring out the vectors that penetrate most deeply and would be most effective in terms of being part of a gene therapy solution. So this is the real goal that the company has, is these optimized vectors by tissue type, optimized vectors. So gene therapy is limited by the body's immune system's response to any engineered virus. Using directed evolution, they've amassed 100 million virus variants that provided technology for numerous diseases. And they need a comprehensive game plan to really identify and prioritize which diseases they should go after, given their limited resources early on in this project. Our analytical approach in this project was to work with the client and experts to really take an initial list of 86 genetic diseases affecting the brain, liver, and eye as high potential value targets, narrowing that down to a workable list at some point, and using expert interviews in that process to do that with a logic that could be followed. And obviously, we'd report the results in 15 weeks. Here's the initial list of 86 genetic diseases, brain, liver, and eye, that this very small startup company was confronted with in terms of figuring out where they needed to land, which of these they had to follow. They could not chase all of these, anything close to all of these. And so we created a screening criteria. The primary screening criteria, the first one, was a hard screening criteria that either the disease met the criteria or it didn't. It was black and white. It wasn't there was no allocation for it being fuzzy. So it had to be monogenic, that is caused by one gene. Size of the gene had to be a relatively modest size because of the variant capability, hereditary, and substantial evidence pointing to a particular gene. That if that wasn't true, it's off the table. Out of those 86, they come out. We also set secondary criteria that was more subject to judgment and required expertise beyond what the team had, beyond what the company had: safety, complexity, treatability, market size, detection, and funding. Those concepts were defined very specifically by the team and the client, but also refined as we went through the interviews with local experts this way. So we had some specific notions of what each of these criteria meant. And here's some sense of the kinds of experts we had access to because of their locality, but also because of Professor Schaefer's relationship with UCSF. And we actually conducted interviews about all of these diseases to really try to evaluate them on the secondary criteria. And this is a scorecard. Coffin-Lowry is a brain disease. This is what we prepared as a result of the team prepared rather, as a result of the interviews, deciding whether or not in every category, whether or not this was a good fit for 4D molecular or not. Okay. So all of the diseases that got past the primary screen ended up with a scorecard. At the end of the day, the team ended up getting through and narrowing this list of 86 or so diseases down to about 21 potential targets for the client that were logically eliminated based on the primary and secondary screening process. And the final recommendation to the company were 4 diseases in each of these categories. However, the team did not feel, and I think we all agreed, it had enough to prioritize within a particular tissue type. They could not say which is 1, 2, and 3 in brain, et cetera, et cetera. But this is a lot better challenge than the 86 diseases they started off with at the beginning of the project.